All right, time for some discrete math. Today, my goal is to finish chapter 4 of the Olowski-Dean text, which is on discrete random variables and also on some specific things that we are interested in when it comes to random variables, like distributions, expectation, and even the standard deviation. And speaking of standard deviation, I wanted to, at the very beginning of this, address that issue exactly. Now, you'll recall that last time there was this mysterious standard deviation thing that we were talking about. Okay, so I at least want to spend a few minutes here on the front end talking about standard deviation, what it is, what it arises from, and why we would care about it at all. Okay, so I'm going to go into the iPad here and deal with that. Okay, so here we go. So over there, we had X, which was distributed as binomial with n trials and proportion of success P. And remember, X was just the number of successes in n trials, okay? And we have these independent Bernoulli trials, if you will. Okay, and one thing that we wrote was that mu, which is the mean, is equal to, right? So by the way, another notation for that is just the expected value of X. That's the way you write that. And this thing is equal to, right? I would sum over all possible outcomes, little x. Okay, so these are supposed to be outcomes, little x. Okay, all possible outcomes, little x. X times the probability of x. Okay, so remember this notation, p of x. This is equal to the probability that capital X is equal to little x. Okay. And you say, okay, well, what are the possible outcomes here? Well, remember, X in this case, like 0 would be as small as it could get, and it could go all the way up to n. Okay, so the range of summation here is just letting the number of successes be anything between 0 and n. And I take the outcome X and I weight it by the probability that it occurs. And I'm telling you, if you do a little bit of algebra here, okay, kind of like we did with that 10 coin flip problem, you're just going to end up getting n times the proportion of success P. And that makes sense. If you wanted to get the number of successes, it makes perfect sense that the average number of successes is going to be the number of trials times the proportion of success. Okay? So, I mean, I'm not going to go into the details here, but right here, there's a bunch of algebra that's almost exactly like, what we did in the case of the 10 coin flip problem. But then there was this mysterious thing, sigma. Okay, this is the Greek letter sigma, okay, which is the standard deviation. So this right here is called the mean or the expected value. Expected value. Okay, sigma, this is the standard deviation, okay? This is the standard deviation, okay? And the claim was that for the binomial, this thing was equal to n p q square root, so raised to the 1/2, where q is equal to 1 minus p, okay? Q is equal to 1 minus p. And it might be kind of mysterious right now what on earth we're even talking about when we say standard deviation. And what I said in our class time together and what I alluded to in the lecture was that the mean is like a one number summary for the data in question. Like if I had to say, okay, if someone said, I am completely unwilling to listen to you talk about the entire distribution, every outcome and the probability that any one of those outcomes occurs. I don't want to look at any pictures. Just give me one number that describes this thing. Well, then that number would probably be the mean, because the mean kind of captures the essence of that in one number. You just weight every outcome by the probability that it occurs, okay? But you know, the mean might not actually be a very good indication of what's going on overall, because the data might be very spread out. It might not hunker down around the mean at all. You know, the mean might not even be a possible number that the random variable could take on. For instance, if I computed the average, or the mean for a die roll, okay, if I computed the mean for a die roll, you know, the outcomes are 1, 2, 3, 4, 5, and 6. The probability of any one of those outcomes is a sixth. So if I compute the expected value of a die roll, you're going to end up with 3.5, which isn't even a possible outcome. You understand? And by the way, in that case, you're not more likely to be close to 3.5 than you are to be way at one of the two extremes, 1 or 6. Okay, so the mean in that case is not a very good indication of necessarily of the overall behavior of the data. And so what sigma is getting at, okay, and by the way, sigma squared is called the variance. Okay, what sigma squared gets at is it actually tries to feel, okay, how good of a measure is the mean as representative of all the possible outcomes. It basically measures how much the random variable is tending to fluctuate away from the mean as a probabilistic entity. Okay, so let's go over here, and I'll actually talk a little bit more about what the variance actually is. Okay, so there's a couple of notations. Okay, so there's like the variance of x. Okay, this is equal to sigma squared. Excuse me. And how is this defined? Well, it's defined by what you do is you take the expected value of a different random variable. You take the expected value of, you take x, and you compare how far away it is from the mean, mu. Okay? But the thing is, I can't just take the expected value of that, because, you know, x as a random variable could be either above or below the mean. And so there's going to be a bunch of positive and negative values that could potentially cancel each other and give us a false impression of how much time x is spending above the mean versus below. That sort of thing would happen in the case of the die roll. If you just computed the expected value of x minus mu, you would get 0. Okay. In fact, that's true for all random variables. If you compute the expected value, if you take x and you subtract the mean, then all the data is going to get shifted down by that amount, and therefore the new mean would actually be 0. Okay, so that's not enough. But I need to, every time x is away from the mean, every time x is away from the mean, I want that to count positively toward the variance. So what I do is I square this. Okay. Oftentimes this is referred to as, you know, the expected, squared deviation. Let me kind of write that down. Okay, so this is sometimes referred to as expected squared deviation. Okay, you're kind of measuring how much x is deviating away from the mean. You're taking the average deviation. Okay, so what is this? Well, okay. I mean, that looks strange to us, right? Well, well, look, this is like the expected value. In fact, let me just write it out. So like this thing is going to be the sum over all possible outcomes, little x. And now my function is no longer just x, like I don't want the expected value of x. Now it's like x minus mu squared, right? So I would take these individual values, x minus mu squared. Those are, that would be one possible outcome for this new function, x minus mu squared. But then I want to weight that by the probability that x occurs. So I get a good impression of how much I'm tending to deviate from the mean on average, okay? And then so watch this. Okay, so this is equal to sum over x. Okay, if I can square this out, so that's going to be x squared minus 2 mu x plus mu squared times p of x. Okay, so there's that. Okay, and here's the thing. This is a sum, so I can like break this thing up. And by the way, mu is a constant, isn't it? Mu is a constant. That's the expected value. That's a number. Okay, so I can kind of treat that as a constant as I break this thing up. So let's go to the next page here. So watch this. This thing is equal to sum over x, right? Again, this is the formula for sigma squared. Okay, so this is the sum over x of what? Of what, right? The first thing was x squared. I can distribute, I could distribute the px through, so this is x squared times p of x. Okay, minus 2 mu, I can kind of pull that out from that other sum, like if you look what's on the previous page, times the sum over x, right, 2 mu x, and then I have to I distributed the p of x to everything, and then it's plus what? Plus mu squared times the sum over x p of x. Okay, if I distribute p of x to the mu of x thing, I still have to take the sum over x, and that's what we end up with. Now here's the thing. This right here, that thing right there, sum over x, p of x, that ought to remind you of something. That's just mu. Okay, that's mu. That's the mean. And what's the sum over x of all the probabilities? Well, that's just 1. Okay, so this thing's there's going to be a massive simplification here. We get that sigma squared is equal to sum over x, x squared times p of x, minus 2 times mu, that's minus 2 mu squared plus mu squared. Minus 2 mu squareds plus a mu squared is minus a mu squared overall. Okay, minus a mu squared. And what's this? What is that? Well, that's really that's the expected value of not x, because the x is now squared. It's the expected value of x squared, okay? It's the expected value of the square of the random variable instead. So look, we get this nice little formula for the variance. Sigma squared is equal to the expected value of the square of x minus mu squared, okay, which is really like the expected value of x with the square on the outside, okay, because that's what mu is, and I square that on the outside. And incidentally, this thing is always, of course, positive, because if you recall at the very beginning, this was the expected value of the square of something. And of course, the average of a square is always going to be bigger than or equal to 0, okay? So this formula right here, okay, this formula right here is what we use to compute the variance. That's what we use to compute the variance for a random variable. And then, but the thing is, if you go back to the previous slide, okay, which was this one right here. Look, suppose that x was like the units were dollars. Well, then the mean is also going to be in dollars. If I take their difference, the mean is still going to be dollars. If I square that, though, which is what's happening here, right? This thing is being squared. If I square that, then the units are no longer dollars, but dollars squared. So the units for the variance, the units are whatever the units were before. It's units squared. Okay, the units are squared for the variance. Okay, so when I go to the standard deviation, right? So the standard deviation, sigma, is just the square root of the variance, right, of x. These are just, right, these things are back to the original units because I've taken the square root, so that I'm comparing apples with apples. If I were to compare ordinary units to squared units, that wouldn't make a lot of sense. So the standard deviation is actually has the same units as the original data. Okay? And again, it's just a measure for how spread out the data is, how much the random variable is tending to deviate away from the mean. Okay, and once again, I just want you to see that we have this little formula for the variance, and of course the standard deviation is just the square root of that. Okay, so that is where, let me just say, well, let me just say this. Okay. Where are we? Here we go. Right. Stop that share. Yeah, that is why that's how we're able to compute this standard deviation in this thing right here. Okay, so I just wanted to spend a little bit of time kind of going through that together. Hopefully that's somewhat helpful. Okay. Well, wait, I need to share this now. Sorry, guys. What I was just saying was, that's how we get this formula right here in the binomial distribution for this. Okay. We compute sigma squared by taking the expected value of x squared, and we subtract off the square of the expected value. And I'm telling you, you get NPQ. Okay. All right. So let's kind of briefly review. We had the binomial distribution. Okay. And then we also had the Poisson distribution. Okay. The Poisson distribution. And the Poisson distribution was sort of strange in that we needed to know the mean before we could even write down the formula for its probability mass function. Okay. And this was the probability mass function for the Poisson right here. Look, it has the mean right there. There's lambda. Lambda is the mean of that thing. And of course, for the binomial, that was our distribution function, right? The probability mass function for the binomial. Okay. So we stopped with these couple of examples. Let's look at this example right here. The chance of having an extra fortune in a fortune cookie is about 3%. Given 144 fortune cookies, we're interested in the number of cookies with an extra fortune. Okay, we might say to ourselves, okay, we know exactly two discrete distributions right now, the binomial and the Poisson. Which of those two seems to best describe this situation? Well, okay, we're wanting to count the number of cookies, and the number of cookies is going to be the number of cookies with an extra fortune. The number of cookies with an extra fortune is going to be between 0 and 144. Now remember, the Poisson distribution can in theory be anything equal to or greater than 0. Here we have an upper limit. So that sort of tells me that we're probably talking about the number of successes in a fixed number of trials. And that, my friends, is the binomial distribution. The binomial distribution. So first of all, 144 trials, proportion of success is 0.03. Okay, X is going to be the number of cookies, or a number of extra fortune cookies. Okay, and what are the possible X values? Well, anywhere between 0 and 144, and its distribution is going to be binomial. Okay, so how many cookies do we expect to have an extra fortune? And find the probability that none do. Okay, find the probability that none do. Okay, how many cookies do we expect to have an extra fortune? And find the probability that none do. So we want that. That's basically asking for the expected value of x, and then the probability that x is equal to 0. Okay, is what we're being asked to find there. Okay, so I'm going to share this screen again, and we'll do a little bit of computation over here. Okay. Here we go. Okay, so back over here. Okay, let's go into the next screen. All right, so x, how did we define it? Well, it was the number of extra fortune cookies in 144, right? There was 144 total trials. Okay, x was, okay, we observed that this has got to be binomial. Okay, where the number of trials is 144 and the proportion of success, okay, that is, what's the probability that we actually have an extra fortune? Well, that was 3%. Okay. X, okay, what's the range of x? Well, x belongs to 0, 1, right, dot, dot, dot. 144, right, would be the maximum allowable thing. We could write down anything we wanted about this. We know all this stuff about the binomial. We could even write down the probability of any amount, yeah. But they wanted to know what the expected number of those things was. Okay, well, the expected value of x, we know that that's going to be NP, okay, which in this case is 3% of 144, right? So it's just 144 times 0.03, okay, which is basically going to be 1.44 times 3, okay? So there you go. That's the expected number of extra fortune cookies. Now, in the last thing that we wanted to compute was the probability that x is 0. Okay. Well, remember the formula for the probability being equal to anything is n choose k, p to the k times 1 minus p to the n minus k. All right. So in this case, it's going to be 144 choose 0 times p to the 0, okay, so that's 0.03 to the 0 times 1 minus p, which is 0.97, to the 144 minus 0. But of course, 144 choose 0 is just 1. So this just ends up being, I mean, in the end, it's just 0.97 raised to the 144th power. And that makes sense because what you're basically doing, right, we could have kind of reasoned that out before even having that formula. What that means is that you're going to each one of the 144 cookies and you're saying, okay, what's the probability that that doesn't have an extra fortune? Well, 97%. What about the next one? 97%, 97%, 97%. And they're all independent, so you can just multiply all of those probabilities together, okay? Okay, whatever that number ends up being. Okay, all right, well, let's go back in here now and move on to the next topic of conversation. Okay. Oops. Sorry, sometimes I'm still fumbling around with this thing. Sorry about that. Okay, so here we go. Find the probability that none do. We already did that, all right? So next distribution is something called the geometric distribution. The geometric distribution, okay? So what's the setup here? Well, I'm still doing these independent Bernoulli trials, okay? and each trial is identical to any of the previous ones. Every single one of the trials either results in success or failure, just like was true for the binomial, okay? Q is the probability of success, or P is the probability of success, Q is the probability of failure. Again, just a bunch of Bernoulli trials once again. Okay, so same sort of setup as the binomial, but this time we keep track of something different. What we're going to do here is we're going to keep doing these Bernoulli trials until we succeed, until we get a success. Okay, so you know, this sort of thing comes up a lot in applications, because a lot of times we will keep doing something until we see something that we wanted happen. Okay, and that's exactly what the geometric distribution is built to deal with. So X is the number of trials until the first success, and by the way, you count all of those failures, which everything was a failure, until that last success. Okay, P is the probability of success. We write X twiddle GO of P to represent that. We have a mean of 1 over P, and we could actually do that. We could figure out why that's the mean if we did a little bit of sum manipulation, but we know, remember, we have the formula for expected value, just X times the probability of X, and we would be able to find that. But we really need to know what the probability of any given value happens to be, and we'll look at that in a minute. And then the standard deviation is given by that formula, 1 over P times 1 over P minus 1, okay? Square root of that. All right, so here's some couple things, you know, just a couple of examples. Keep trying until you make a free throw, okay? So every one of those trials is independent. I keep shooting until I make a free throw, okay? Or maybe keep shooting until you miss a free throw. You count the total number of free throws, including that last miss, okay? That would be a geometric distribution, okay? There's a silly example about coffee shops. Keep trying different coffee shops till you find the perfect coffee, okay? Other examples, right? I mean, you know, so like in the actuarial science discipline, where you're trying to determine what you should charge as a premium to one of your customers for their insurance, you know, maybe each year you have a probability that they will have no accidents, okay? And you just know that from previous data. You know, this person that has these particular you know, features about them, including age, you know, whatever it is, they are this likely to have an accident, okay? Well, how long are we going to have to wait until they actually have an accident? How many years? Well, each year would be like its own Bernoulli trial. You know what I'm saying? Each year would be like its own Bernoulli trial, and you would be wanting to see, okay, how many years are going to go by until the first accident occurs? That is where the insurance company is going to have to actually pay out, okay? So this distribution comes up even in the actuarial discipline, where people are trying to come up with reasonable insurance rates to make sure they don't go bankrupt or something, okay? Here's the formula for the geometric distribution. And let's think about why this is the case. It's not really that hard. So what's the probability that X could be equal to K? And by the way, K could be any non-negative integer. K could be any positive integer, yes, because it's the number of trials here. It's the number of trials until the first success, and you count both of those things. Count the failures and the first success. Okay, so actually, let me just kind of fix this right now, okay? In here, let me fix this right now. Non-negative, so it's not just non-negative integer, it has to be positive. For K, a positive integer, right? Because I have to perform a trial in order for there to be a success. You know what I'm saying? Okay, so we save that and then we'll go back in here. Okay. Okay, so why is this the formula? Well, I mean, like, what is the probability that x is equal to 1? Well, if x is 1, that means I had a success right away. So that's just p, yeah? And this formula works for that. That would be 1 minus p to the 0 times p. Okay, well, what's the probability that x is 2? Well, x being 2 means I had a failure on the first trial and then a success on the second. What's that probability? Well, that would be q times p, which is 1 minus p to the first times p. Okay, and that's the same thing as 1 minus p to the 2 minus 1 times p. And you could see why all of these would have that extra factor of p at the end, because the last success or the last trial is a success and the other ones are all failures. And now you kind of see the general pattern. In order to have k total trials, I had to have k minus 1 failures in the initial, followed by a success. So 1 minus p is for the first failure, 1 minus p for the second failure, dot, 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 1 minus p for the k minus first failure. If you multiply all those together, it's going to be 1 minus p to the k minus 1. Then you have the success that happens with probability p. And you multiply those together because of independence. Okay, so there's the geometric PDF. Hopefully that kind of makes sense. Okay. So, I mean, if I wanted to have 10 total trials, you know, for me to get one success, then that means I had 9 failures and then 1 success, 9 failures and then 1 success. So then I would see q to the 9th times p, and that's exactly what this formula is saying. Okay. So last example, and we're going to be done here. Suppose that you are looking for a student at your college who lives within 5 miles of you. You know that 5% of the 3,500 students do live within 5 miles of you. You randomly contact students from the college until one says he or she lives within 5 miles of you. What is the probability that you need to contact at least 4 people? At least 4 people. Okay, what is the expected value of the number of people you have to contact? Okay, so do you see here? Here you're doing this trial, namely contacting a random student, okay, independently, until you finally get to one that actually lives within 5 miles of you. Now, in order for this thing to be perfectly modeled by the geometric, you have to assume that that you could potentially call the same person 2 times in a row. Okay, so you're having a computer like randomly dial numbers and not keep track of who's been called before. Okay, so that would preserve independence. Otherwise, this problem would be too complicated. Okay, so 3,500 students. Okay, 5% chance that, so a 5% chance that you're going to you know, stumble upon one that actually does live within 5 miles of you. Okay, and actually what's strange here is because of the nature of the fact that we don't keep track of who we've called, I could in theory have to keep calling forever. Does that make sense? I could have to make, you know, 37,000 calls because I might keep calling like the same student over and over again, or the same, you know, few students. Okay, so this does have the geometric distribution, but the weird thing is I could potentially call any positive integer number of students. Okay, so let's go over and work this out a little bit. Okay, what's the probability I'm going to have to contact at least 4 students? Okay, I think was one of the questions. Is that right? Let me see here. What is the probability that you need to contact at least 4 people? Yes. Okay, so let me go in here and share this, and then we'll finish up with this example here. Okay, here we go. Okay, so what am I doing here? So X is going to be equal to the number of students contacted. Okay. P, this is equal to the probability that a student lives within 5 miles of you. And that was given to us to be 0.05. 0.05. So this X right here, X is distributed as geometric with proportion of success P, okay? So in this case, it's geometric with proportion of success 0.05. Okay, the expected number of students we're gonna have to contact, that's the mean. The expected number of students we're gonna have to contact, that's the mean. That's 1 over P. Why does 1 over P make sense? Okay, well, think about it. So in this case, if there's a 5% chance that if there's a 5% chance that I'm going to have to, that I'm going to contact a student who lives within 5 miles of me, then I expect to have to contact, I guess, about 20 students before I stumble upon one that actually does live within 5 miles of me. Okay, and that's exactly what we get here. Okay, 1 over 0.05 is 20. Okay, and that makes sense to us. And again, like so suppose that my geometric distribution was like flipping a coin until I get heads. Okay, so I just flip it forever until I get a heads, and then I count the total number of coin flips that I had to execute. Well, the probability of success in that case is 1/2. And what's the expected number of flips? Well, according to this formula, it's 1 over 1/2, which is 2. Okay, so and that makes sense that we would expect like maybe 2 flips to have to happen in order to get a heads. Okay, and there was one more question that we had, and that was, what is the probability? What is the probability that I have to contact at least 4 students? And that's the probability that X is greater than or equal to 4. Okay. Well, remember, let's use P and Q here. Just I know that P is 0.05 and Q is 0.95, but let's use P and Q just for convenience. Okay, so that would be like P of 4 plus P of 5 plus P of 6 plus dot 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 dot. Yeah. So what would that be? That would be, so P of 4. Now remember, we actually wrote down the PDF for this thing. That would mean 3 failures followed by a success. So that would be Q cubed times P, right? That means 3 failures followed by a success. What about P, the probability of 5? Well, that means 4 failures. So Q to the 4th times P plus, what about P of 6? Well, that's Q to the 5th times P plus dot, 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 dot. Now, notice I have a common factor that I can pull out here, and that's Q cubed P. Q cubed times P. Okay, and what's left behind? Well, there would be a 1 left behind from the first term. What will be left behind from the second term? Well, Q. What about from the third term? Well, Q squared. Okay, and this is a geometric sum. That's where this random variable gets its name. This is a geometric series. And do you remember from Calc 2, if I have 1 plus x squared, etc., that adds up to 1 over 1 minus x, so long as x is in absolute value smaller than 1. And in this case, that's true because q is a probability. So this is actually equal to q cubed times p times 1 over 1 minus q. Okay? But what's 1 minus q? Well, that's p, right? That's p. That's p. So this p right here cancels this stuff down here. And what are we left with? Q cubed. Okay, after all that simplification, we get q cubed. So that's very interesting. So let's think about that for a minute. So let me go to the next page. So in other words, the probability that we have to contact at least 4 students ends up being equal to q cubed. And by the way, that computation we just did, that would work no matter what. Like for instance, note the following. We would have what? Like the probability that x is equal to or greater than anything, any little x, this would be equal to q to the x minus 1 by the exact same argument we just gave. There was nothing special about 4, okay? We could have made that exact same argument in this case. Okay, so but it's equal to q cubed, which means what was q equal to? Q is equal to 0.95 to the third. Okay. So what this is, but this makes sense. Think about it. Let's sort of just talk about why this makes sense. Okay, what is the probability that I'm going to have to contact at least 4 students? Well, what that means is that the first 3 students I contact aren't within 5 miles of me. Okay, and that happens independently. Okay, so what's the probability that the first person isn't within 5 miles? 0.95. What about the second? 0.95. Third, 0.95. And at that moment, I have guaranteed that I'm going to have to contact at least 4 students. So the probability I'm going to have to contact at least 4 students is the same as the probability that I start with 3 students who are not within 5 miles of me, which is 0.95 times 0.95 times 0.95. Okay, so this probability makes sense. Makes sense to us when we think about it. Okay. All right. So I am going to stop. I am going to stop this right here. And that, my friends, is the end of chapter 4 of Olowski-Dean. Okay, so as you know, I've sent the test out to you. Again, you could come to class time or office hours if you want to ask, some specific questions about that. I'm going to have to be careful about what I say exactly, but I can always give some clarifying remarks. Maybe if you'd like me to review something, I could potentially do that. But yeah, just keep pressing on. You guys are doing a great job. We're in this together. We'll get through this together. And incidentally, after this week, I'm going to start giving homework sets out of the Olowski-Dean text. This week, you have this test to work on, so you have plenty going on right now. But I'm going to start giving homework quizzes out of that other text. Okay? That's all for now.